our October seminar. If you're not aware of or if this is your first time attending, we put together a monthly seminar that is open to anybody, and we usually restrict it to some general statistical topics for researchers at all levels. We at Stat Central do this. We also provide some statistical consulting advice for researchers across the university. So you can put in a request on our website to talk with one of us and help you out with your research project. And we also provide a service where particular units or schools across the university can have in-depth statistical support by contracting us out for a period of time. So if you're lucky enough to be in one of those schools or units, you probably already know that. Otherwise, if you need to talk to us about an arrangement such as that or a contract for a particular project, we're happy to discuss details with you. Today we have Peter Humburg, one of our consultants, who's going to be talking to us about bootstrapping. And this is not a technique that we tend to go over in our intro stats courses. So this might be really new to a lot of you, but it can help us do some really great things when we get into trouble with our actual data analysis. When we are presented with actual data, it's not always amenable to all those easy things that we learned in our classes. So Peter's going to talk to us about what bootstrapping is and how we can do it. Peter, take it away.
Thanks, Nancy. And welcome, everyone. I hope you can see my screen now. So yes, so I thought I'd talk to you today a little bit about bootstrapping and how it can help us out, well, what it is anyway, and how it might be useful. And yeah, as Nancy said, it's a little bit outside of maybe the well-trodden paths of our usual introductory offerings. So I'll try to take it slow, but ask questions if you get confused and it just doesn't make sense anymore. Yes, so what's the problem we are trying to solve here? As you are probably aware, when you're doing sort of statistical analysis, you often rely on quite a few assumptions. And when we are looking at little sort of example data sets in an introductory stats course, then often those assumptions are quite reasonable, and it all kind of works out, and that's great. And in fact, in many situations, things do work out well enough, and it's fine. But sometimes data isn't that well behaved, right? So things aren't always normally distributed and things like that. So when you come into contact with real-world data, if you like, sometimes things don't work so well anymore, or maybe you suspect that they don't work so well anymore, and can't be quite sure. You've probably heard of sort of non-parametric tests, which you might use in those cases, right? So if if assumptions look dubious, then let's just use a test that doesn't use those assumptions. That's of course also a reasonable thing to do, but it can limit a little bit what we can do, right? Because it's fairly easy to find a non-parametric test for sort of simple comparisons, but if your analysis requires something more complex, then it's quite possible that there isn't really any good, ready-made non-parametric test that you can just plug in. So what you're going to do? And while we're talking about assumptions, it's maybe worth noting that often you don't even quite know whether your assumptions are violated or not, because they don't apply necessarily to your data directly, but they might apply to the distribution of your test statistic, right? So if you're, say, doing a t-test and you are making assumptions about how the mean of your sample is distributed, but you only have one sample. You basically know nothing about the distribution of its mean because you have a single observation there, right? So you can look at your data and it may or may not look like that's a reasonable assumption, but it can be hard to be sure, right? So it's easy to find yourself in a situation where you want to do this analysis, you want to do it right, but there are a number of assumptions and things look a bit dodgy, right? And you kind of rather not rely on assumptions that may turn out to be unreasonable. Now, I don't want to scale too much, right? So it's there are quite a lot of cases where actually you're fine. And especially if you're dealing with sort of symmetric distributions, often things work out quite well. But sometimes you do have to worry, and today those are kind of the cases that we're talking about, right? It doesn't mean that you always have to worry, but sometimes you do. And then you might have to make some extra effort, like Baron Münchhausen here, who is pulling himself and his horse out of a swamp by his ponytail, I think. And instead of ponytails, we're going to pull ourselves up by our bootstraps by making the most out of what we've got. So the general idea is that, well, we've got some data. Right, so we've gone out and collected some data to study a specific population that you're interested in. So you got your sample. And now, this sample, well, if it's a representative sample from the population, then maybe it's not so unreasonable to think that you could learn a little bit more about the population by making that data that you have work a little bit harder. So the general argument here is that we're just gonna treat our sample as if it would behave the same way as the population, and then see what we can make of it. How are we going to do that? So we have a sample of some size, right? Maybe it's small, maybe it's large. It doesn't really matter that much. It's whatever size it is. Hopefully large enough for what you're trying to do. And then for this sample, we can calculate any sort of statistic we might be interested in, say its mean. And then we can go back to the data and take another sample from our sample, if you like. So we are resampling the data by drawing, another n of our observations. One observation for each observation in our original sample, but we're gonna do this with replacement, so that each individual observation in our original data set might turn up multiple times in the resampled data set, or not at all, right? So we're going to get a new mix of observations, but they all come from the original data set. And then for this new sample that we just created for ourselves, we can calculate the mean again, or whatever other statistics you might be interested in. Well, now we have two of them, if you like, and then we can do it again and again and again, quite a lot of times. And that gives us then a large number of resampled data sets. And each of those now has its own mean and everything, allowing us to look at how much that might vary between different samples that we take from the population. Okay, that's maybe all a little bit abstract. So let's look at an example and see what happens. So here is a small data set that I've dug up. It is quite an old data set, I guess. It's from 1882 or so. When Michelson and Morley went and tried to measure the speed of light by bouncing a light pulse between some mirrors and measuring the time it took. And if these numbers here look kind of small, that's because a large number, 299,000 kilometers per second, has been subtracted from them. So we get some easier to read numbers, okay? And so what they did in the experiment is they took 20 measurements. And as you can see, these measurements, they varied quite a bit. And we can probably agree that this looks like a slightly odd distribution, right? They don't seem terribly nicely behaved. So we might worry that sort of, typical assumptions we might make are maybe not that appropriate. Okay. So the first thing we can do is, we can try to, use these measurements to get an estimate of the speed of light, right? And so this then here turns out to be, if you take the mean of all the measurements, that's 831.5. So that's, 299,831.5 kilometers per second. And that's well and good, but I think it's fair to say that there's some uncertainty in this measurement, right? And so maybe it might be interesting to have a confidence interval around that. And one way to get that is with bootstrapping. So we do what I said just before and start resampling this data set, right? We have 20 observations to begin with, so we're gonna draw 20 of those, all of those 20 observations. We get a new data set, we calculate the mean, and we do it again and again and again. Here I did it about 1,000 times, I think. And then we get a distribution of the means of this, of these data sets. Which you can see here. So these turn out to be, well, maybe not quite symmetric. They seem to be a little bit skewed. But pretty much around the mean of the original data set. And now one way to get a confidence interval for this is to simply go and look at the corresponding percentiles of this distribution here. So if we find the 2.5 and 97.5 percentile, then that will give us a 95% confidence interval for the mean. And there are, sorry, there we go. So this gives us some idea of where we might expect maybe the actual speed of light to fall. And having confidence intervals is quite useful, of course, but often you're also interested in doing a test, right? So you want a null hypothesis test to compare either two groups or your measurement, in this case, maybe your measurement with a different measurement. And so just continuing this example, we could ask, well, is there, in a sort of attempt to figure out, whether this measurement of the speed of light is any good, is there sufficient evidence to say that the measurement, the speed of light they determined based on this experiment is actually different from the one that is our current best estimate, which is on the scale that this data set is on 792.5. And using our Bootstrap estimates that we already got, right? So you got our Bootstrap samples of all these different means. And we can now get a sort of simple test by comparing. So we start out by comparing our estimate, which is 831.5, to the one we want to compare to, which is 790.5. And so there's 39 units apart. So we can look at the data that we've sampled at our the means from our Bootstrap samples, and we can see how often does it happen, basically, that we are that far out from the mean. Now, there is a small problem with that, because we obviously have generated these Bootstrap samples based on a sample that was based on these observations, not on what you might consider, the null hypothesis. So we have to make some assumptions here. So back to making assumptions. And the assumption we make is that we can take this distribution and shift it. So we take the distribution of our Bootstrap means and shift it to where we think the null distribution is going to be located. Well, not where we think, but that's what we determine, right? What the null is. And then base our comparison on that. And that's all fine as long as we think it is reasonable to believe that the sort of general shape of the null distribution is the same as the distribution that we observed, basically. And if that is, vaguely true, then we get a reasonable sort of approximation of the null distribution of these means. And then we can again just look at how often would we expect it to happen that our observation falls, in this case, 39 points away from the mean. And it turns out it's not very common. And we'll end up with a p-value of 0.01. Which means that in my 1,000 samples here, that happened about once. Okay, so that's so far so good, I guess. We did manage to get a p-value and do our testing and get a confidence interval, everything, without having to assume that anything is normally distributed or things like that. But we did have to make the assumption that we can just take this bootstrap distribution and shift it to work as the null. And that's not always reasonable, right? And obviously, people recognize this, and for a while, I've developed better ways of doing this. And I just want to take a few minutes to illustrate one of those. But there are somewhat maybe more complicated and sophisticated ways of doing this that you might use in practice, right? But so one first improvement is to use what is called a studentized bootstrap. And here the idea is that instead of working with the means directly, where we compute the mean for each of our bootstrap samples, we compute the t-statistics basically, right? So instead of computing all the means first and then doing the comparison we're interested in, we can do that comparison for each sample individually. We'll get then a distribution of t-values that we can use. And we can base confidence intervals and t-values on that, which is sort of, seems like it's just doing the same thing, right? And we again can do all the other calculations kind of as before and look at the extreme observations and how many of those there are, and get a p-value, which in this case turns out to be exactly the same, but that is by no means guaranteed. And that's great. It might not be immediately obvious why this is better. And in fact, we do have introduced a maybe additional complication here, if you think about it a little bit. Because so one of the reasons it is better is that we get a more robust estimate, if you like. And the way we get this is by dividing the difference here. Oh, sorry, you can't see where I'm pointing, I think. By dividing the difference here by the standard error of the mean, right? Which, of course, we have to estimate. So we get a more robust estimate, but to be able to get there, there's another quantity we need to estimate. And how do we get an estimate for this standard error? Well, bootstrapping, of course. So we can go and for each of our bootstrap samples, right? We create a bootstrap sample, we can calculate the mean of that, that's fine. But then to know, or to get an estimate of what the error of that mean is, we need then to go and do another round of bootstrapping. So now for each sample, we are creating another set of bootstrap samples. So you might do another 1,000 each, say. And then you can look at those, and that will tell you about the variance in that estimate, and that will give you your standard error. So that obviously gets pretty expensive fairly quickly. So if you do 1,000 bootstrap samples of your original sample and then do 1,000 bootstrap samples of each of those to get the standard errors, then you've done 1,000,000 samples, right? And that was fine for this small example here. I mean, it runs a second or so, right? But if you have more complex models you're working with, and possibly more data too, then you can run into situations where you get to do lots of resampling, and that can be slow. The question is, why is it better? I already hinted at it a little bit, and why is it that much better that we are willing to go through all this trouble? It's obviously less sensitive to outliers, because when you get samples that are a little bit, that are a little bit of an outlier, sort of, a bit unusual, they will also typically have large variance. And so that, they will have a large standard error, and that puts everything a bit more to the middle, if you like. And in general, it turns out that these that then for these distribution of the t-values that you get there, it is often more reasonable to assume that these are a reasonable approximation of the null, so that you then can be a bit more confident in using them for your inference. So that is one example how you can make the Bootstrap procedure a little bit more complex and robust, maybe. There are other types of Bootstrap that you might want to use. I'm not going to go into detail, although, yeah, I think I have a slide later where we at least mention them. But before we get there, I just wanted to point out one other thing that you need to worry about, which maybe isn't so apparent in this simple example, where we just have one set of numbers and look at the mean. But in real life, if you like, when you have more complex data sets and you do resampling, any sort of resampling, whether it's bootstrapping or something else, you have to make sure that you kind of take account of the structure in your data, right? So if there's some correlation structure, relationships between the observations, that is important, then you might want to keep these. You need to do the resampling in a way that that is preserved. And here do have the a mention of the bias corrected and accelerated bootstrap, which is a even better version, if you like, which is able to deal with the situation where maybe your data isn't, well, your bootstrap samples aren't that well behaved, if you like. They generally, well behaved means here that your bootstrap distribution, sort of the distribution of your bootstrap value is symmetric and hopefully centered on the sample estimate, which is not guaranteed to be the case. And also, of course, there is this tricky issue that you might think that you would quite like to use the bootstrap when you have a small sample, because then it's particularly dubious that your sort of assumptions of normality and things like that hold. But if you have a really small sample to work with, it also means you kind of have, your sample is only a very small window on the population. And that then can make you a bit blind to the more extreme values that could exist there. Some of the variation that exists in the population may not turn up in your sample. And of course, it also means you're taking small samples when you're resampling, and those could then turn out to be pretty atypical if you're unlucky. And so, oops, sorry, things are being a bit weird here. Yes, so that's the well, sort of a general introduction to the bootstrap, if you like. But you might ask yourself, well, how am I ever going to do this myself? And the good news is that there is bootstrap functionality built into most stats packages that you might want to use. So for example, if you use SPSS, for many of its modules, it has the option to use bootstrap estimates. Here I grabbed a screenshot of the linear regression, and you see there's this bootstrap button which then allows you to get your bootstrap confidence intervals. And you see that one of the options here is the bias corrected accelerated bootstrap that I mentioned at the end. And the other one is the percentile bootstrap, which is the one I initially talked about. And in ARM, we have lots of options. There's a boot package that does, whoa, what happened? There's the boot package that does sort of general bootstrap duty, and it does support some fairly tricky data like your time series or sensor data. If you want an easy way to bootstrap your linear model fits, there's Simple Boot, which will do that out of the box, I think. If you're working with mixed models, then LME4 has the boot now function. And in SAS, you can kind of resample your data and then use sort of by group processing to get bootstrap estimates. And Stata has the bootstrap command to get to Bootstrap your estimates that you generated before. All right, so I think that brings us to the end, and I'm happy to answer your questions.
Thank you, Peter. I think we have a few questions, but maybe Eve has been answering them for the most part in the chat. Does anyone want to unmute themselves and answer a question? Sorry, ask a question. Even if you've already typed it into the chat, if you feel like.
I'd love to, Jordana. I'd very much like to. Peter, thank you. That was really clear and really kind of crystallized my ideas. I've always been, I mean, I'm a maths teacher. I understand central limit theorem, statistics and so on. And it's always been a bit of black magic to me, bootstrapping, because how you can infer, you've got one sample and you don't know if that sample represents the population. And then you're doing some jiggery pokery with that sample, and then you can be more sure about the population. So it just doesn't make any sense. And some of those assumptions you were talking about make really clear sense to me, which is that, I mean, look, you take a sample of the population, let's say it's an entirely biased sample, it's a 1 in a million sample or 1 in 1,000 sample, and it's incredibly skewed. And then you're taking subpopulations or subsamples of that sample, you're not going to get a representative mean or any parameter for the population. So I think that what you said was really clear to me, that you know, bootstrapping will only work if basically your sample is big enough and broadly representative of the population. Am I is that correct, or am I just missing?
Yeah, so I think you have to assume that your sample is representative of the population you want to study, right? And in a way, you have to assume that anyway, right? If you don't get a representative sample, then anything you infer from that sample doesn't really apply to the population because the sample wasn't representative, right? So you can really only learn things about the population you actually sampled. And it is, of course, possible that that's different from the population that you intended to sample. So you do have to be a little bit careful there. And so, yeah, of course, I mean, the larger your sample is, the more you kind of learn about the population. That's kind of generally true, right? And there is, yeah, as I said, if you have a very small sample, there is a risk that there are just bits of the population you're completely missing, right? And you're just blind to those. But it can work, you know, reasonably well with fairly small samples, but you do have to be a bit more careful, yeah.
Yeah, so sorry, I could just add something here, Peter, if that's okay. Yeah, so the notion of whether or not something's representative is unrelated to sample size. For a sample to be representative of a population, it's just got to be sampled in a way that captures the key. So an IID sample for population is technically it's one where every individual in the population has the same chance of being included in the sample. So a sample of size 2 can be representative of the population in the sense that if you were to in the sense that every possible individual in the population has a chance of being in the sample. And
that's not the same thing as representative there. That's just talking about random sampling.
Yeah, well, representative, what we mean by representative is not about sample size.
Yes, but if you're calculating parameters from your sample and you're saying they're representative of the population, they can't be representative of the population if they're entirely, you know, skewed from the population.
Okay, so if you just say take 2 observations from a population and you estimate an average from it, that can be representative. That is representative of the population mean, in the sense that it will be centered on the right answer if you sample appropriately, if you sample so that every individual in the population has the same chance of being there.
Yeah, so I mean, this is more about how you sample rather than how many you sample, right?
Yeah, exactly.
So if you intend to study the general population, but you recruit all your participants from university students, then you might get a large sample, right? But they will be different in various ways from the general population because it's, they're not representative of the general population, regardless of how large your sample is.
Yeah, so I think it's worth laboring this point. I think, Lisa, I'm not talking about ability. That's a different thing again. But yeah, I think in the chat, there was a bit of confusion about when you can apply the bootstrap. It's like, well, if you need it to be representative, that means your sample size is big, but if your sample size is big, you can use central limit theorem. So what's the point of the bootstrap? There was kind of this sort of argument happening. But yeah, for something to be representative doesn't mean sample size needs to be big. The main place where bootstrap is useful is when central limit theorem you don't think is going to work for you. So sample size is small, or your distribution is very non-normal, or some combination of the two.
Right. Thank you so much, David. Can I just chip in a little? So if let's say for a certain class of estimator that don't use averages and central limit theorem is not going to work too well, then using normal approximation of the sampling distribution will be problematic. So I think under those situations, bootstrapping is pretty good. And I'm just kind of want to follow up on the discussion. What happens now if I have sample selection? So there are many methods to address for sample selection, I don't know, maybe matching or some selection models or some sort. Then under that situation, how do we know the sampling distribution of whatever statistics that we are interested in will it still be well approximated in this kind of bootstrapping procedures? Under what situation will a bootstrapping procedures of this sort be a better approximation of the sampling distribution than our large sample approximation using central limit theorem? I just try to know when I should be considering applying bootstrapping in approximating the sampling distribution.
Yeah, I'm not sure I quite got all the nuances you're after there. So but I mean, in general, I mean, yeah, if you think that the central limit theorem will apply basically on, if you are confident that making the required assumptions is fine, then you're it's fine to do that. But yeah, as David said, in situations where that's maybe questionable, because either your sample is small or well, and what small means here varies a bit on the context, right? For example, if if your data is very skewed, maybe a sample would have to be quite large for you to for the central limit theorem to save you, if you like. And then a bootstrap estimates might be safer, but I'm not sure whether that quite answers your question.
So I'm thinking, let's say for example, let's consider some classes of estimator whereby we don't use averages. Okay, so let's move away from the OLS kind of estimator. So some, I don't know, median-based estimator. And now I'm just kind of, and I estimated, and perhaps I'm not very sure about what is the sampling distribution of my estimate under this class of estimator. And now what happened under that situation in observational data studies, whereby my sample, I suspect, is not representative of the population. That means there is sample selection bias. That means IID assumption is being violated. So how do I then use Bootstrap? Should I be using Bootstrap? What should I be thinking about? How to overcome this? So I'm in the paradigm whereby I already agree with you that I'm not going to think about a particular class of estimator. So I'm like, Bootstrap is good, but in the event of sample selection, what should I be doing?
Yeah, so I think, yeah, the question is, when do you use a Bootstrap, right? It's like,
Yeah.
that's basically the question. When would you use a Bootstrap? So, I think there was a mention in there, when would you use the Bootstrap instead of relying on central limit theorem? Well, you would use the Bootstrap when you're not confident the central limit theorem is going to work for you, is the short answer. And when does the central limit theorem not work? When sample size is small and you're not confident about your normality assumption. So that was where Peter started from. Like sort of he had a, you've got a small data set, we don't have enough information to know if normality is satisfied, or a bit worried about it. That's a good place to use the Bootstrap. The other main place people use it is when they're doing, using methods where you don't actually use central limit theorem, like it doesn't apply for some statistic you're using. That's the other place.
Because why I say sample selection. So for example, I have a bad draw of a sample that is maybe extreme because it's observational data study. So now what I'm doing is I'm drawing sample within that sample to approximate the sampling distribution of my estimate or statistics. Then, I mean, that potentially involves some form of assumption. I think IID is one of the assumptions necessary for bootstrapping, or is it not? So I'm just thinking about, there must be assumption related to Bootstrap and assumption related to my large sample approximation. And I want to kind of understand the trade-off between these assumptions so that at least I could think about when I should be using Bootstrap, how should I be using Bootstrap, and so on and so forth. That's what I'm actually, asking.
Okay, so I guess both of them, both the central limit theorem and the Bootstrap, assume your data's IID.
Right.
But they work well in different situations. So the central limit theorem, it is a normal approximation, and it works better the closer your data are to normal.
Not necessary, right? I mean, for the mean.
In general, it works better the closer your data are to normal, but it also works eventually if your sample size is big enough.
Right.
Right. Mm-hmm. So Bootstrap, it works better as your sample size increases, but it's not connected to the idea of normality at all. So if your data is quite non-normal, it can still work quite well for you.
Sorry, can I just interrupt that? I thought the whole thing about the central limit theorem was it didn't matter what the distribution of the actual population was. If you take enough samples, the distribution of a particular parameter, let's say the sample mean, will be normally distributed, provided, blah, 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 the sample's large enough, blah, blah, blah. So that's what I thought bootstrapping was. I thought you're just taking subsamples of your sample, and then eventually you end up with this nice normal distribution. Isn't that based on the central limit theorem?
Okay, so the central limit theorem, it says, yes, if your sample size is big enough, something will be approximately normal, but it doesn't assume, but yeah, there's a question of how well it works and when it doesn't work. So
but it's the distribution of the sample parameter, it's not the actual sample.
Yeah, that's right. Yes.
Yeah, yes. So you've only got one sample. So I'm a bit confused why you're saying like the central limit theorem applies or doesn't apply, because you've only got one sample. But the bootstrapping, you've got multiple samples. So that's using the central limit theorem, isn't it?
Okay, so when we talk about when it applies or doesn't apply, we're thinking about what the true distribution of our data is. The problem is we don't ever know that in practice. We've only got a sample. But if our true distribution of our data was strongly skewed, central limit theorem doesn't work as well. And you can get a hint for whether your true distribution is strongly skewed by looking at your sample and seeing if it's strongly skewed.
But as n gets bigger, the approximation will be better. I think what perhaps David is saying that maybe the approximation, the convergence rate might differ depending on the distribution.
Yes, that's right. So your n would need to be bigger, the more skewed your data was for it to work. So if you got 10 observations, maybe central limit theorem will work for you if your data is not that skewed. But how confident are we that our data is not skewed based on just looking at 10 observations? So that's the sort of that's one main place where you use it. But whereas the central limit theorem doesn't work well when our data is skewed, the Bootstrap is not as sensitive to this issue. I mean, it's based on a different idea and a different set of theory. I mean, the theory behind it is basically saying that our sample is an estimate of the true distribution. And so it's not saying our distribution is normal or it is anything else. So it's not going to be as sensitive to, like, it's not worried about skewness or outliers in the same way.
Yeah, so maybe one way to think about this is that when you use the central limit theorem, you make the assumption, you make an assumption of normality, right? So you're basically saying the sampling distribution is going to be normal. But with the Bootstrap, instead, you're trying to approximate that distribution based on, resampling your data and looking at the distributions of the test statistics you compute again and again. So that's different, and you then don't have, it doesn't have to be normal. You're using a sort of empirical distribution.
Yeah, so Gary asks if it's about precision rather than accuracy, the Bootstrap. I don't know, it depends what we mean. Precision or accuracy of what? If you're talking about a statistic, you're estimating a statistic, then it's not affecting its accuracy, it's affecting your estimate of the uncertainty of it. So in that sense, I guess so. Yeah. Someone asked for code. Have you got something?
Will certain data structure, not so much about the distribution, but maybe there are some form of dependence or clustering in the cross-section or in panel, whereby there are some form of persistent autocorrelation, whereby then bootstrapping might be more useful?
So you're saying that there's serial correlation in the data is bootstrapping?
Yeah, it could be serial correlation. It could also be dependence in the cross section. So
yeah, so Bootstrap has an IID assumption, or at least the conventional Bootstrap. If you don't have the IID assumption, so for example, if you have serial correlation, then you can try and bootstrap, but you got to bootstrap groups of observations using sort of a block bootstrap or something like that.
Yeah, so
and it's a bit messy, and it's not my preferred way to go. Yes, but because there's a question of how big your block size should be and all the rest. Eve's actually done a fair bit of work on that. She did a PhD looking at this stuff, so she's a good person. She's been answering questions in the chat, and is a good person to talk to about trying to apply the bootstrap when you move outside of the IID context.
are we waiting for Eve?
Yeah. So I mean, maybe.
I was just saying she'd be good to talk to about it.
Yeah.
Right.
Yes. So maybe we should leave it there. I think we are at the end of our allotted hour.